right, good evening, folks. Welcome to the Starco Planetarium. My name is Eric Johnson. I'm the director here, and I'm so glad you all have braved the rain to come out and join us for the final edition of the Kaler Science Lecture Series for the academic year. So anyways, if you've never been to one of these events before, the Kaler Science Lecture Series originally started as the World of Science Lecture Series, where even though the planetarium, a lot of people ostensibly think we only show stuff with astronomy in here, we liked to bring experts in several different scientific fields to show off their areas of expertise, to give you a sense of that world of science. One of those speakers that would present here at the lecture series every year was Jim Kaler. He would talk often about astronomy, but also various other atmospheric phenomena, and he was a beloved speaker who presented here for almost 30 years. And so after he had retired from that, we renamed the lecture series in his honor. So anyways, this evening's speaker, he is here with us, of course. That is Dr. Mohan Sankaran. He is a professor in the Department of Nuclear, Plasma, and Radiological Engineering at the University of Illinois. Before joining us in 2020 in Central Illinois, he had gotten his post-secondary education out in California, specifically Southern California, as a matter of fact. He went to UCLA for his bachelor's degree, and he got a PhD at Caltech. He had served as a professor at Case Western Reserve University out in Cleveland before joining us here at UIUC. Welcome, folks. Anyways, I really am looking forward to this because he was very interested in showing you all some examples of how we see plasmas out in nature. So I'm going to head back over to the console and present to you folks some of those examples. Sorry to step on the point you were about to make, my apologies, but I just wanted to show you how excited I was to be a part of this talk. All right, Dr. Sankaran, thank you so much for coming out here, and the floor is yours.
Great. So yeah, thanks to Eric for inviting me to give one of these Kaler lectures today. Thanks to all of you for coming again in the kind of the not so great weather outside. I was just telling our camera person that at Illinois we have the engineering open house going on today and tomorrow too, and that also has been affected by weather, unfortunately, but people are still coming, so that's great. Today I'm going to be talking about some of the work that we're doing related to ammonia and food. And from the title, and I'll tell you, I'll fully admit that from my own work, there isn't really a direct connection to astronomy or astrophysics or space necessarily. But I'm talking in this beautiful planetarium, which I normally don't give lectures like this in a place like this. So I did want to make a connection to something that we can take advantage of this beautiful facility. And there is something actually. There's an easy connection that I can make with my research, which has to do with plasmas. As I'll talk about today, the way that we actually are tackling this problem of making ammonia and making food is by using plasmas. And that's really what my research focuses on. So as Eric said, I'm going to start with some examples of plasmas that are out in space that allow us to use this planetarium. So we'll start with the first video here, which is to go really far out in space. I'm going to start out far away from Earth first with the first example.
The iconic Ring Nebula lies in the summer constellation Lyra. This glowing ring of gas is the result of the death of a sun-like star. As the star runs out of fuel, intense radiation from its core heats the outer layers and they escape into space. The nebula turns out to have a much more complex shape than we can see from Earth. The main structure of the nebula is a broad ring of nitrogen. That's the red ring you see. Hotter oxygen gas is seen here in green and fills the interior. What's even hotter still is helium, and it's seen here as blue oblong lobes perpendicular to the nebula's main structure. A number of dense, dark knots of gas circle the inside of the red nitrogen ring and have so far resisted the blast of stellar winds and radiation. The shadows of these knots can be seen as long, thin spikes around the ring. Glowing hydrogen also reveals the inner and outer halo lobes, which formed when the star began to burn out. This detailed three-dimensional model of the Ring Nebula will help astronomers understand the last stages of a star's life. Our sun is expected to have a similar fate in about 5 billion years.
Great, so there was a wonderful narration there that explained how you have gases there that are ionized because of the UV light that's being emitted by the star, and then the ionized gas is what we refer to as a plasma. So now we're going to come closer to Earth and show another example of a plasma. So this is the next video here. This one doesn't have a narration, so I'm gonna talk over this. So hopefully as you see this, it immediately becomes familiar. I think we were very fortunate here in Champaign, even in the last year, to be able to see this. Usually you have to go to Iceland or somewhere far up north. So this is, of course, the Aurora Borealis, or known as the Northern Lights. So let me explain a little bit about this if you don't know what this is caused by. So this is a phenomena that's at the kind of the poles of the Earth, and it's caused by particles that come from the sun through solar wind. And these are charged particles and so on that come, but when they come to the Earth's surface, they get attracted to the magnetosphere. And there they then start to gain energy, and then they transfer their energy to some of the gases in our atmosphere, oxygen and nitrogen. And then the glow that you see here is the oxygen and nitrogen that's being excited. And I'll talk about why you get this light in a little bit. But it's not so different than the Ring Nebula. It's an ionized gas, except now it's the atmosphere of the Earth that's being excited. So this final example, if you can kind of focus on kind of at the bottom, you can probably see it's lightning. Okay, so I don't even have to show this video today. There was some lightning, I think, in the last few hours, so you've probably witnessed it yourself, but I didn't know what kind of day it was going to be, so I wanted to remind you. Now, lightning, let me explain what it is first of all. It's particles that charge in the clouds and the atmosphere, but in this case, it's usually water and ice that charge from rubbing. Now, those particles, when they charge up, they create very strong electric fields, and if the electric field is strong enough, it causes something called breakdown. The gas, air, breaks down, and you form ionized gas, and as a result of the ionized gas, you're able to conduct electricity, and the electric field dissipates through lightning, through this current flow that creates lightning. But the lightning itself is a plasma because you are ionizing the air as it forms. Now, lightning is a good example because all of us know about it, even if we haven't, for example, been lucky enough to see the aurora. But in addition to that, it connects to my talk today because lightning is a natural example of fixing nitrogen. So farmers have always kind of prayed for rain, but also for lightning because they know that they get a little bit better plant or crop growth when there's some lightning. And the reason for that is that you can actually take the nitrogen and form something, nitrates, which can actually act as a fertilizer, a natural fertilizer, so you don't have to actually get your own fertilizer. So that's a connection to some of the things I'm going to be talking about today. I want to continue with some examples though, because I want to show you kind of how widespread plasmas are, not just in nature or way far out in space. Plasmas are also around us in labs, in industry, making things that we use every day. So let me give a few examples. The first example might be a little dated now, which is the plasma television. I don't know if anyone remembers this, but when flat panel TVs first came out, one of the technologies was something called a plasma TV. The plasma there was actually used as the backlighting. It would create UV light, and then the UV light would excite a molecule to create the red, green, blue that would then show the image on the screen. Now, over time, this got superseded by LEDs, which were able to create the red, green, blue on their own, and you didn't need this plasma there. Another example in technology is welding. So plasmas can be at very high temperature, so you can melt metal and bond metal, so it's still used today to weld metals. And then fusion. So some of you who may be watching the news, you know that in the next few decades, we may have these fusion reactors that mimic the star or the sun on Earth to create energy. So in a fusion process, you actually have a plasma, and through the reactions, you get heat released, and that heat can then be used either directly or to power something that creates electricity. And this could be a very safe and clean form of electricity compared to fossil fuels. The final example I want to give is the microelectronic chip. So this is in all of the things that we use every day, right? Cell phones and laptops. But what you might not be aware of is that the way that these chips are made, the materials that make up the electronic device that functions as your processor or your memory, is actually because of plasmas. Plasmas are used as a chemical process to etch and deposit all the materials that make up those devices. And if it wasn't for plasmas, you wouldn't be able to have these incredibly fast devices. Okay, so these are kind of the examples to motivate why plasmas are so important and so ubiquitous, really. Let me now back up and talk a little bit more about what a plasma is. So one way we can think of plasmas is to connect it to other phases of matter. So I think all of you probably remember that there's 3 phases, right? Solid, liquid, and gas. And we can connect these by saying that they're kind of linked by temperature. So if you start with a solid and you heat it up, eventually you get a liquid, like boiling water. On a stove, you eventually get a gas, right? So if you keep heating, you go from solid, liquid to gas. And what happens on a molecular level is that as you heat up a solid, those molecules gain energy and then they slowly start moving apart. So in a liquid, they start moving apart a little bit, and then if you keep heating it up, they gain enough energy to move completely apart, and they'll occupy like the whole volume in this room, right? Well, if you keep heating up a gas, the next thing that could happen is that you can actually knock off electrons from the molecule. And at that point, you end up with ions and electrons, not just the gas molecules. And this is what defines a plasma. Now, this can happen in different ways. I'm showing this with temperature. In the Ring Nebula, it happened by UV. So the UV is what knocked off the electrons. And then in the case of, for example, the aurora, it was the solar wind that hit the atmosphere and caused the ionization. So this can happen with different energy and forces, but in the end, you end up with this ionized gas in all cases. Now, there's an important point that I want to make about plasmas, which is that they contain energy. So you form them, and once you form them, you actually have a source of energy. So let me use hydrogen as an example. So if you create a hydrogen plasma, it's made up of ions and electrons, but it's also made up of the hydrogen itself, and the hydrogen could have, for example, hydrogen atoms that are formed from the hydrogen molecule that breaks apart. Now, those hydrogen atoms are a good example because they're really simple, just 1 proton and 1 electron. Those hydrogen atoms can be in the ground state, or they can actually be excited to higher levels. And that's what I mean by exciting molecules or atoms. So what that means in terms of their actual structure is that the electron can occupy different orbitals. There's different configurations that are possible. That 1 electron can either be in the ground state, which is referred to as n equals 1 in the quantum number notation, or it can be in an orbital that's further away from the nucleus, n equals 2, or 3, or so on. And if it's completely out, it's ionized, okay? But it can still be a hydrogen atom, neutral, with the electron slightly excited to a higher level. And coming back to why you get this light from a plasma, it's because when you have something excited, it will eventually relax, and when it relaxes, there's an energy released, and the energy releases in the form of a photon. So when a hydrogen atom has an electron in the n equals 3 and it relaxes to n equals 2, you end up seeing red or pink light. And so in that Ring Nebula, they mentioned the outer part was pink. That's from these types of relaxation processes. And that's the same reason why you see this pink-red glow in this discharge here. But if you actually looked at this spectroscopically, you'd see a lot of different colors, and some of them are weaker. That's why you don't see them. And those are all the different states that are there. So temperature and energy is a common underlying characteristic of all plasmas. And this actually allows us to unify all these different plasmas that we just saw. So we can, for example, on one plot with temperature, show where you would have things that are in space, things that are on Earth, like lightning, space, and then even in the lab, like the arc discharges that are used for welding, or this is a glow discharge that you could use in the lab for some application. The differences between these are basically that they all have different temperatures or energies. So, for example, lightning has a very high temperature compared to the nebula and things like that we were looking at. Okay, so this is one way to categorize it by temperature. And then the other property that we can use is the number of particles, the number of electrons and ions that you have, which is referred to as the density of the plasma. So this is a nice way to kind of show all together all these different types of plasmas. So these are very diverse. They have lots of different properties, but they're all plasmas. Now, this is energy. I want to then introduce one other important thing that you should be aware of. Plasmas don't just contain energetic particles, they also have a lot of chemical reactions going on. And those chemical reactions could then be coupled to the energy in the plasma. And the example I want to start with for a chemical reaction is what happens in the sun. So the sun is also a plasma, but it's a very special plasma because you have these reactions happening that generate all the heat and light that, of course, on Earth we take advantage of. Now, just to go a little bit through the reactions, so the sun has a lot of hydrogen. The hydrogen can form these hydrogen atoms that I talked about, and these could react together, and one of the protons can transform into a neutron, and if that happens, then you end up with this what's called heavy hydrogen, deuterium. The deuterium can then continue to react with another hydrogen, a proton, to create helium, which is an isotope here, helium-3, and then those helium-3s can continue to react to eventually form kind of a normal helium-4 that we're familiar with 2 neutrons and 2 protons. These reactions, if they happen, will release heat and light, and that's what allows the sun to create all that heat and light, this reaction occurring on the surface. The reason that you get this heat and light is because you're going from a large number of molecules, small, to a fewer number large molecules. So this is called a fusion reaction. Okay, so this is the same thing that we're trying to do with the fusion devices on Earth, but we don't normally do it with these specific atoms. We actually do it with deuterium and tritium because that reaction is easier to happen. The sun is at such a high temperature that you can't really do that on Earth. So in order to work at a lower temperature, we have to use a different chemistry. But the idea is the same. So this is a reaction that happens naturally out in the sun, but it motivates the idea that you can use plasmas purposefully for chemical reactions on Earth. So the other example I want to give is something that is very historically important. So in the 18th century, a German scientist, Siemens, wanted to make a chemical, ozone, which is shown here as O3. I'll talk a little bit about why he wanted to make ozone, but what he came up with eventually was a plasma process. So the plasma was formed here in this schematic. He fed it oxygen, and then he applied electric fields like lightning to break apart the oxygen. The oxygen breaks and forms atomic oxygen, and those atomic oxygens then can continue to react to form ozone. Ozone was used for water treatment. That's what he was interested in. And even now, all water treatment plants have a plasma process to produce the ozone and clean the water. So a very important chemical reaction, a chemical process, and it's done by a plasma. Now this is my segue to the main focus of my talk, which is using plasmas to make important chemicals. So ozone is kind of a solved problem. So I started thinking about, what other chemicals could we make with a plasma? And if you kind of generally look at what are some important chemicals, this is a plot from the International Energy Agency, what you'll see is that the most important chemical for us to use is ammonia. And the reason for that is that ammonia is basically a component of fertilizer that is used to grow the food that sustains the whole world's population. So there really is no more important chemical for our livelihood than ammonia. So this is sort of the motivation, can we use a plasma for ammonia? But before we get to that, let's talk about how ammonia is made today. So obviously, ammonia, this is the actual production volume. It's already made on a very large scale. So how is that done? So in the 1930s, again, 2 Germans, Haber and Bosch, came up with a chemical process to make ammonia. And this video is showing you what basically happens. You have nitrogen and hydrogen reacting on the surface of a catalyst, usually iron. And through those reactions, eventually the nitrogen breaks, the hydrogen breaks, and then the N and the H come together, and you end up with NH3, which is ammonia. Now, besides needing a catalyst, this requires very high temperatures. The reason for that is that the molecule nitrogen is a triple bond, if you saw it carefully in that video, and it's really hard to break. So you not only need a catalyst, but you also need very high temperature to break that bond to get the reaction to go. Now, when you go to those high temperatures, unfortunately, you also have to go to very high pressures. So going back to your high school chemistry, if you remember, there was something called Le Chatelier's principle, and that's kind of a definition of equilibrium. It basically says that if you have a reaction that goes from more molecules to less, it needs higher pressure to get it to go towards the product side. So this ends up needing hundreds of atmosphere, hundreds of times normal atmosphere. So it's a very difficult reaction to run, but it works beautifully the way that Haber-Bosch did it. Now, one of the key points is the hydrogen. So nitrogen can come from air. You can just separate the nitrogen from air and you've got it. But the hydrogen, where do you get it from? So the hydrogen actually currently comes from methane. So you take methane and you do another reaction called methane reforming. You react it with water and you can get hydrogen. And then the hydrogen is fed eventually into the Haber-Bosch reactor with nitrogen to make ammonia. Okay, so this is how people now make it. It's a very large process, complicated, lots of steps, but it works. Okay, you can react and make ammonia, and that's how all the ammonia is made in the world today. Now, one of the consequences of using methane as the source of hydrogen is that carbon there has to go somewhere, and what it ends up as is CO2. So there's a CO2 penalty for making ammonia. About 1 kilogram of ammonia, you make about 1 kilogram of CO2. So this translates into some carbon footprint for all the food that we eat because it's grown with ammonia, right? So for example, a loaf of bread, about half of the weight of the loaf of bread is equivalent to the CO2 that was coming from the ammonia that was made to grow the bread. So that's the bad. The CO2 is not all bad. It's used for carbonation. So the beer we drink, most of the carbonation comes from CO2. And this is so important that a couple years ago, you might have seen a big world crisis. During the World Cup, especially in the UK, pubs ran out of beer. And the reason they ran out of beer is because they couldn't get CO2. And the reason they couldn't get CO2 is because the ammonia plants had shut down in the area. So the CO2 shortage led to not having beer. Okay, so that's partly a joke, but the CO2 is something that is a problem actually for the carbon that's resulting from this process. There are some other issues that I want to point out as well. I mentioned that the plant is pretty large and complex. The plant is really large, and one of the reasons the plant is really large is that in order to make this energy efficient, you have to go to very large scale. So roughly, you have to make the plant about 1,000 tons per day, production of ammonia, in order for it to be energy efficient. So these plants have to be really big. In fact, so big that you might be surprised that worldwide, there's only about 100 of these plants. So all that ammonia that we get for all the food that we make comes from about 100 plants. On top of that, they're really concentrated in a few places. So we're very fortunate that in the United States, we have a large majority of those 100 plants. And then there's a few other regions of the world that also have them. But there are a lot of places in the world that don't have many plants. For example, Africa. And it's particularly a problem in places like that because African soil is not very fertile. So they really need fertilizer, and yet they don't really have access to ammonia. There's one more issue with it, which is that even in the US, the plants are in certain locations and the ammonia has to be transported. Ammonia is not that safe. So ammonia, the way it's used in the United States is anhydrous, no water, liquid in these large tanks. And if they get released, they're toxic. So right here near our backyard in Illinois, there was a truck accident about a year ago, and the ammonia spill ended up killing 5 people. So this is a problem related to not only how it's made, but also how it has to be transported to the point of use. So although ammonia is made currently at the production rates that supply our food and everything, there's a need to maybe rethink how we make the ammonia and how we use it. So I'm not the only one. There are many people in the scientific community trying to reimagine how to make ammonia. So the vision that I and others have is, can we first make ammonia by an electrified process? So electricity, like fusion, wind, these are going to start coming online in future years, and there are a carbon-free, clean source of input compared to using heat and fossil fuels to produce that heat. Then we want to use sustainable, readily available feedstocks that don't require other processes. So instead of hydrogen, can we use water as a source of hydrogen? And then you want to react these all together, right? So we need a process that's electrified that can react these type of feedstocks and then eventually make ammonia. So this is kind of the vision for what we want to do. Now, these types of electrochemical processes are already used for some applications. So, for example, if you want to make hydrogen, people are already starting to think about how to use an electrochemical process rather than methane to make hydrogen. And the way that you do that is with this type of system where you have these electrodes dipped in a solution and you apply a voltage and you can create reactions at the electrodes. So in this case, water can be split and you can end up with hydrogen being produced from the water. So can we do the same thing with ammonia? Can we have nitrogen and try to react it with water in this system to make ammonia? Unfortunately, it doesn't work. And the reason for that is that the way that these processes work is that there's a metal at the surface of one of those electrodes that actually catalyzes the reaction. And in the case of trying to reduce nitrogen to ammonia, all the metals that have been used preferentially reduce the water to hydrogen before they reduce the nitrogen to ammonia. So people have been trying this for a few decades now, and you just can't make ammonia. So how can we kind of try to do this? Well, there is actually an example in history where ammonia, or not ammonia, but nitrogen was reacted, and it was using a plasma. So in the early 19th century, Birkeland and Ide, two Norwegians, created a plasma and was able to fix nitrogen. But the reaction was a little different than making ammonia. The nitrogen and oxygen in the air reacted together to form nitric oxide. And then the nitric oxide could be further reacted to make nitrates, and the nitrates were used as a fertilizer. But this shows that a plasma can actually react nitrogen. It can fix nitrogen just like the Haber-Bosch process. Now, interestingly enough, this process was developed before Haber-Bosch, about 30 years before. But it did not continue. And the reason for that is that this process used electricity, and at the time, electricity was really hard to get. So in Norway, they were lucky because they had hydroelectric power, but in other countries, there was no electricity available. So when the Industrial Revolution happened, and it was possible to use fossil fuels to generate heat, the Haber-Bosch process was much easier, and it took off. And also, as time went by, it became very efficient at making ammonia, and we never looked back. But one of the points I want to make is that times are changing again, and electricity is becoming easier and more readily available, and so processes like the Birkeland Ide might be revisited in trying to fix nitrogen. So we are working on this problem, but we have a slightly different approach than Birkeland Ide, and I want to introduce that for the next few slides. So we had been working on a process somewhat similar to electrochemistry, like what I showed for breaking water. So we had been using a plasma with electrochemistry, and this is a video of one of our experiments. So we're not doing anything with nitrogen in this case. We just set it up. We had a plasma here, and we had an electrode here, and they were contacting water, and we ran voltage and current through the system. Because we were using gold, what you're seeing happening here is it's actually changing color, and that has to do with the reactions that are going on with the gold. So what we're actually doing is reducing gold to gold particles, and that's giving off this pink glow. It's the same thing that you'll see in stained glass in churches. The color you see is from the metal particles like gold. The pink is from gold, and that's exactly what we were doing. The point here is that we can have reactions occurring in this process. And it's just like a conventional electrochemical cell, but we've replaced one of the electrodes with a plasma. And so now there's reactions happening with a plasma and the rest of the system. So we decided that maybe this could be used to react nitrogen. So this is the more details of what we do. We have nitrogen coming in, we have a plasma, an electrochemical cell. This is electrically powered, so no heat. We have this running at atmospheric pressure and room temperature. Now, compared to berklinide, we initially had the idea of taking the nitrogen, reacting it with the water, and making ammonia, not nitrates. So that was our original goal. And why would this work compared to the electrochemical cells that I said did not work at all for making ammonia? Well, we don't use a metal electrode. We use a plasma. So it's sort of a hybrid between berklinide and what electrochemists were trying to do. So the short story is this works. This type of approach to trying to make ammonia actually does work. These are experiments here, and we did some controls, and the basic point is that when we have nitrogen in our process, we get ammonia being made. When we don't use nitrogen, we don't see any ammonia, so there's no contamination and so on. The other exciting thing is I mentioned that there are two competing reactions that typically happen in these systems. You can either reduce nitrogen or reduce water that gives you hydrogen. So we tried to compare those reactions in our process, and we use a figure of merit here called Faraday efficiency to compare those two. And we were able to see that at some conditions we can get 100% efficiency for the ammonia, meaning that we have completely stopped the competing reaction, which was not able to be done in a typical electrochemical system. So that's the good news, okay? But there was some bad news. The bad news is that in our system, not only does nitrogen get reduced, even though that's what we're trying to do, we also get oxidation. So unfortunately, plasmas, because there is so much energy, can drive a lot of different chemical reactions. And when you have nitrogen and water, you not only create hydrogen to form ammonia, but you also form these oxygen species like hydroxide, hydroxyl, and those react with nitrogen to give you oxidized products such as nitrate and nitrite. So we end up with a mixture of these in many of the cases. So very recently, we have been trying to address this, and we came up with an idea. We realized that it was hard to just make ammonia, but it was actually pretty easy to come up with a way to make just the oxidized form of nitrate. We do that by just changing to air. So when we use air, we get almost exclusively nitrates. And once you get nitrates, those are actually pretty easy to reduce by a traditional electrochemical process. They're much easier to reduce than nitrogen. So if we add an electrocatalyst in our process, we have another electrode where we can add that, the nitrate can get reduced to ammonia. So it's two steps. We go from nitrogen to nitrate to ammonia, but at the end, we end up with ammonia. So this is something that we're now working on. Now I'm going to spend the last few minutes talking about sort of a different direction that we're taking our work. So we can make ammonia, we can make nitrates. These could be directly used as fertilizers to grow plants. But even that process is energy intensive. It has more carbon cost involved, and it's also time consuming. So think about all the time that it takes for us to grow food. And all the energy that's involved has to do with the land and all the equipment that has to be used. So this plot shows sort of the different amounts of CO2 that are produced for all the different types of food that we eat. So it's not just the ammonia, but it's also the other aspects of it. And one particular thing I want to point out is that meat is very costly. Proteins, very costly to have to cultivate. So is there a different way to imagine making food? So I'm part of a project at Illinois. It's funded by DARPA, a government agency. The program is called Cornucopia. And the idea of this program is to go from some of our basic, readily available resources like air, water, and in the future electricity, and go all the way to making food, and not traditionally, by a chemical process. So how would we do this? So we would start with these components of air and water. We would react them to form some substrates, like ammonia or a carbon substrate. These substrates can then be fed to a microbial process. And in the microbial process, these substrates are upgraded to macromolecules that are basically the components of food, like fat, protein, carbohydrates, and so on. And then you can do some further processing to tune the taste and texture, and you can end up with some food that is edible. We're not talking about making like a McDonald's hamburger. We're talking about making like a shake or a jerky that has all the important constituents of food to provide you calories and energy. Now this would be more sustainable, should be faster. We can do this, whenever we need it. So this is a whole new way of thinking about making food. Now this microbial process is sort of the key part of this, and I don't want to spend too much time on it, but let me give you a little taste of how this works. So in these microbial processes, again, you start with these sources of nitrogen and carbon, and then there's a very complex network of biochemical processes that are going on before you end up with proteins and carbohydrates. So for example, ammonia goes through a step where you get glutamine, and glutamine is an amino acid, building block of proteins. The glutamine will continue to react to form other amino acids. The ammonia is also involved in making nucleic acids, the building block of DNA, and then the DNA is involved in helping making proteins from the amino acids. So that's how you end up with proteins. I won't talk too much about the other things, but the ammonia and the carbon source together will end up with things like carbohydrates and lipids. Okay, so this is how you end up with food through this process. Now this might sound like science fiction. It did to me when I first talked to bioengineers on campus to see how this would work, but this is already happening. Okay, so there's a company, Triton Algae, that uses an organism, algae, and they're already making synthetically something that tastes like pork. Okay, and I think some of you might be familiar with these Odwalla shakes that have this green color, and there's an additive to make that green. It's a protein additive that is actually made from algae, from chlorella. Okay, so this is already coming out on the market, but in these cases, you're not feeding nitrogen from a plasma process yet. They're still using whatever is already out there. Okay, so our goal was to try to integrate all of this all together. So we're just starting this, we're in the middle of it, but I'll show you some of the type of work we're doing. So we picked a microorganism my collaborator works on. This is a bacteria, E. coli Nissel 1917, a very safe one. And we took our plasma-made sample, here's what the plasma sample contained, and we showed that we can grow the E. coli. Now when it grows, it builds up mass, and that mass contains the protein and carbohydrate and so on. So the fact that we can see the cells grow is an indication that we are making the components of food. Now our plasma sample was as good as commercial nitrogen. This means the commercial nitrated and ammonia that's made by Haber-Bosch. But we made ours from just air, water, and electricity. And then if we don't have any nitrogen, these bacteria just don't grow at all. You have to have nitrogen for them to allow to grow. Now, we also tried some other samples. So remember that, depending on how we run our plasma, we might get some different amounts of ammonia and nitrate. So here's an example where we made mostly nitrate. In this case, it still works, but not as well. There's a little bit of a delay. These cells have to adapt before they're able to use the nitrate. Ammonia is a little bit better than nitrate, but eventually they do grow. Now, if we made a slightly different version containing mostly nitrite, it actually doesn't work at all. So this sort of is like a negative result, right? But there's something else exciting even from this result, because this was one type of bacteria. If we change the type of bacteria to a different strain, we do see growth with that exact same sample that didn't work with the other strain. And this motivates kind of the last idea that I want to share, which is that our work is actually going hand in hand with these bioengineers, because we can try to optimize what we make for a particular microorganism, or the microorganism can actually be genetically engineered to better utilize what we make with our plasma process. And that's the way that we see our research going in the future. Okay, so with that, I think I'm hopefully on time and leaving time maybe for questions. I want to thank all of the collaborators, students, and postdocs that have been involved in this work over the years, and of course the funding agencies that supported the work. And with that, again, I thank you for taking the time to come hear about my research, and I'll be happy to answer any questions you may have.
All right, thank you, Dr. Sankaran. If any of you have questions, please raise your hands. I will bring the microphone over to you so you can ask them, okay?
I know the Haber-Bosch process is used to make ammonia, which I'm pretty sure is also used to make explosives. So is there any like ethical concerns that you have for your process, since it's so at least to me, it seems so simple and easily to be reproduced and kind of small scale?
Yes, that's a very good question. It has come up in actually the funding and the way that we're doing the work. I'll just clarify that the Haber-Bosch process makes ammonia, and I don't think ammonia itself is an explosive, but you can go on to make ammonium nitrate, and that is the one that is a problem. So this actually came up in our work because ammonium nitrate is considered, like you said, a potential explosive, and it actually comes under something called a classified, unclassified type research project. At least the way that we were able to avoid any issues is making sure that we don't make anything dry and we make it dilute enough. So as long as we're working on ammonium nitrate in a certain way, we were able to avoid any issues. But maybe in the broader context, yes, this could be a way to show someone how to make this, and that could lead to issues. I can't really say much more than that because, the process itself is not that difficult, and there's enough papers out there now that I don't think we're doing anything that would teach anything new to anyone. But that's how we were able to at least do the research ourselves.
You mentioned that much of the soil in Africa is not very fertile. Mm-hmm. Would your food process be practical to establish throughout Africa to provide more food for a growing population that wants more protein and higher grade food? Yeah,
so maybe I'll answer that in a couple different parts. So although the soil is not fertile, I think if there was fertilizer, you could make it be able to better grow plants. So the idea was that I think there was only a couple Haber-Bosch plants in Africa, the whole continent. So if we could make more fertilizer there through some other way, not large plants, but kind of my idea was to make them on a smaller scale, then you can have more fertilizer, and maybe you can make the soil have the ability to grow plants. So that's one idea. The other idea, I think that maybe you were implying at the end, is we could even maybe potentially make food, right? Not just fertilizer. So with the other process that we're working on in remote places, we could make food itself, because we'd have this whole integrated process to start by making the fixed nitrogen, but then also have this microbial process to continue and make food. So our goal is not to make food for the whole planet, but it's to supplement making food in places or in times of need. So one of the things we've been talking about is disaster relief. In those cases, maybe making food this way, or in deserts and places where you can't grow easily. So, yeah.
Well, if you would go directly to making food, I'm thinking about avoiding the idea of fertilizer runoff mm-hmm. in areas, and you would maybe bypass that and not end up with problems like we have in the Gulf.
That's a great point. That's right. And I'll also even say that these smaller scale reactors could also help with addressing that issue. So one of the issues with the way that ammonia is transported and used, there's such a cost to transporting and everything that it tends to be overused. So one of the ideas that we're thinking about is if we have these smaller reactors, you can make fertilizer and apply it kind of more locally and intermittently. And maybe that will reduce over-fertilizing and the runoff.
All right, let's thank Dr. Sankaran again for coming out here. This is really entertaining. Thank you so much. Again, I want to thank you all for coming out to join us for the Kaler Science Lecture Series all throughout this academic year. We'll resume these once again this fall in October. In the meantime, if any of you were planning to stick around for our April feature show, which is Expedition Reef, I would ask that you folks step outside as well, and I will reopen the doors right around 8 o'clock. And feel free to consider joining any of our other programs on Saturday afternoons throughout this month as well. Unfortunately, I don't have any summer schedules ready for you all, but I look forward to sharing that with you all very soon. Have a wonderful rest of your night. Stay dry, folks. Thank you once again.